Hey guys, so today we're going to be going ahead taking a look at applications of Newton's second law. So if you remember, Newton has three laws that make up his basic laws of motion, and we've already gone over the applications of the first law, which is when we go ahead and take a look at object in motion tends to stay in motion, object at rest tends to stay at rest unless acted upon by an outside force. And we talked about the concept of inertia. So today we're going to be looking at applications of Newton's second law, which if you remember is the law that's going to go ahead and take a look at F equals ma, the mathematical piece of these three laws that we can go ahead and use for calculating. And you'll go ahead and get a chance to do that today as we go ahead and go through. So let's start with our essential questions. Number one, what is Newton's second law and what benefit does it give to physicists? I think we kind of already answered that just in our little prologue. Number two, what is momentum? Number three, what is impulse? And number four, how are momentum, impulse, and Newton's second law related to each other? Now, we're not going to complete our discussion on momentum and impulse here. As we continue to move throughout this term and into the next term, we'll go ahead and take a look at momentum and impulse in more detail as we go ahead and start tying them together in terms of collisions and starting to look at transfer of energy when we start looking at objects. But today we're going to do a simple introduction to these two concepts as they fit in with Newton's second law. All right, so what exactly is Newton's second law? According to Newton's second law, acceleration is produced when a force acts on a mass. The greater the mass of the object being accelerated, the greater the amount of force needed to accelerate that object. And this is typically expressed with the mathematical equation, which remember we've talked a lot about how equations are actually relationships between the variables. And so F equals ma. In all practical senses, you've already kind of know how this works. If I'm going to go ahead and push, say, a rock or a box across the floor, a heavier box is going to require me to push more. A lighter box is going to require me to push less. And so these are the things that we're going to go ahead and take a look at in terms of how we calculate, and we can tie this in with what we've already done in terms of our kinematic equations and the relationship of all of our different variables if we think about units. Okay, remember, derived units are very important when we start looking at all of these characteristics. Okay. Now, if Newton's first law identified that forces were what started and stopped motion, it's Newton's second law that supplied the missing link between force and acceleration. Technically speaking, Newton equated force to the differential change in momentum per unit time, where momentum is a characteristic of a moving body determined by the product of its mass and velocity. So in simplest terms, when we go ahead and take a look at momentum, okay, let's put this into a mathematical equation, and we'll come back to this later on, remember. Okay, maybe I should switch to white here. So momentum, okay, which we typically are going to go ahead and represent by like a rho or p, is going to be determined by the mass times the velocity. Okay, so momentum is equal to mass times velocity. And we'll come back to this later on. And so this is the direct relationship that Newton applies, but we have taken this and extrapolated it because we'll take a look at these units later on to F equals ma, where F is a force equals the mass times the acceleration. Okay, so we'll come back to momentum and impulse later on, but just to kind of keep you started. Okay, so to determine the differential change in momentum per unit time, Newton developed a new type of math called differential calculus. So those of you who are in pre-calc or are in calculus right now, IB Calc, his original equation looked something like this. So F equals m times delta V over delta T, which remember delta represents a change in, and we should know at this point, just from what we've done in our previous units, that a change in velocity over a change in time is what we call acceleration. Okay, so because acceleration is defined as the instantaneous change in velocity, in an instant of time, the equation is often rewritten in the format that we're more familiar with. This also allows us to better specify a unit for force. Now, this is where it gets a little tricky because most of us don't think of force in terms of the units that we use in physics. When we use force, we're typically thinking of like pound foot of force. We're thinking about these Americanized units that we use for automobiles. But a Newton is a really useful unit because it's related to a kilogram, which remember is our SI unit for mass. And so if we're going to do F equals ma, mass in kilograms times acceleration, which should be meters per second squared is our standard base unit, a kilogram meter per second squared is going to be our Newton. All right. So that's a lot to kind of write in, but that's the unit that we start looking at. So if we think about this, and here, let's make sure it's still white. If we think about F as in force is equal to mass times acceleration, where mass is in kilograms, acceleration from the previous page is Vf minus Vi, change in velocity, right, over t time. So if we look at these units, velocity is in meters per second minus meters per second all over seconds. So we're looking at kilogram meter per second squared. And that's our unit when we go ahead and take a look at, that's going to be a kg. Okay. So that's our unit that we start looking at. So get used to a Newton because we're going to go ahead and use it a lot. This is going to be a common unit for the rest of this unit, and not just this unit, this term. All right. Okay. Now, Newton's second law is concerned with net forces. Now, let's think about the difference between net and gross. If we have a free body, so we can do a quick little free body diagram here. If we have a free body, and I have the center of mass or center of gravity, we have a force going up, something like the normal force. We have weight, F of g, which equals weight, F normal. We can go ahead and start looking at, we'll call this F applied, and this will go be F of friction, force of friction. We're not worried about all of these forces. We're worried about the net force. So if we add all these up together, what is our net force going to look like? And so if we redraw this just with our F net, you can see that the force applied outweighs the force of friction, and then the force, normal force and the weight balance each other out. So this is the force that we would be looking at. And so in terms of our F equals ma, what we're really looking at is F net equals mass times the acceleration. The mass doesn't change from one drawing to the next, but the acceleration is going to be based on the force, the net force applied, which is going to send the box in this direction. And so this is where, again, those free body diagrams are really helpful in letting us solve these equations, especially if we start thinking about direction. So if the force is applied to the left and the motion of the object is applied to the right, it's going to be a decelerating force. All right. So we can think about like Spider-Man or Superman trying to stop a train. As that train's moving forward, they're pushing or applying a force to it, but that force is being applied in the opposite direction, causing it to decelerate. Okay. So keep these things in mind as we kind of go through. We'll get some practice problems and you'll see how all of this works out. So if you use the same force to push a truck or push a car, the car will have more acceleration than the truck because it has less mass. It's easier to push an empty shopping cart than a full one because the full shopping cart has more mass than the empty one. So the more force is required to push a heavier mass. Now at this point, I'd like you to go ahead and move on and take a little break from this video and oops, too far, and go watch the Ed puzzle on Newton's second law in the NFL. It'll get you to really start thinking about how force and mass and acceleration are related to each other. And you'll also go ahead and get a chance to be introduced to momentum and impulse, which we'll talk a little bit more on the next couple of slides. So Go watch the Ed puzzle on Newton's second law, and then we'll come back in here and finish up. Okay, welcome back. All right, I hope you guys enjoyed that video. Let's talk a little bit about momentum. So when you're in sports, especially contact sports, momentum is a commonly used term. And we have some idea probably of how this works and what it means. When you're looking at a team that says, oh, and they have the momentum going in the playoffs, they're on the move. It's going to take some effort to stop them because they're in sync, they're working well. So a team that has a lot of momentum is hard to stop. In physics, momentum has a similar meaning. It refers to the quantity of motion that an object has and how difficult it's going to be to stop it. So if we look at it in these terms, we can really think of momentum as mass in motion. So all objects have a mass. Matter has mass, as we've talked about it. So if that mass is moving, then it has momentum. And mathematically speaking, if we go ahead and start looking at this, momentum, which we're going to represent here by rho equals mass times velocity. Okay, so the unit that we're going to look at for momentum is mass in kilograms and velocity meters per second. So a kilogram meter per second is our unit for momentum. We will talk more about this in our next unit as we go and finish off this term, and then we'll go ahead and look at impulse as well. But that's the basics of what you need to look at. You think about how fast something is moving and how much stuff is moving. The combination makes up the mass in motion or the momentum. So if I have, a tiny little girl that's going to go ahead and roll down the hill on her roller skates, she can get a lot of speed, which increases her momentum, but her mass isn't going to change. And so she's never going to have as much momentum as the same increase in speed of a huge football player going down the hill in the same roller skates. Okay, so kind of keep that in mind. It's a combination of both mass and when we go ahead and start taking a look at velocity. Now in football, this is where if you have enough speed coming at somebody, you don't have to be huge because you're going to use your momentum of whatever mass you have and all that speed to go ahead and make the collision to try and make the tackle or break through the tackle. So in some cases, they really like the super fast medium weight running backs because if they can get out in open field, they get moving so quickly that they still have a lot of momentum even though they're not as big. And so a combination of mass and velocity. All right. So what's impulse then? So if mass in motion is momentum, impulse is going to be the force over a certain amount of time. And from the video, hopefully you recognize this as well. Well, the units should make some sense here too. So if the units on the previous one made sense, this shouldn't be a big stretch for you. So I'm just going to use I here. It's not quite the appropriate term, but we're going to use that just for now. So impulse is going to be equal to force times time. Now let's think about the units here. Force is in newtons. So that's a kilogram meter per second squared. Okay. And that's going to be times time. Let's go ahead and undo that really quickly. There we go. And so that's going to be times time, which is in seconds. Now this is important because when we go ahead and cancel this, we're left with seconds on the bottom and this one cancels out for a unit of kilogram meter per second. And that should look familiar to you. That is the same unit that we had when we took a look at momentum, kilogram meter per second. All right. So there is a relationship between impulse, force times time, and momentum, mass times velocity. So the impulse caused by a force during a specific time interval is equal to the body's change in momentum. And this will come into play when we go ahead and take a look at it in our next unit. So effectively, impulse is a change in momentum. So this can also equal change in momentum. And we'll play with that more in our next unit. Okay. We will discuss this more when we get to collisions, but this is a good introduction. I think you have the basic ideas for what you need here. All right. So let's talk about what we've talked about in terms of Newton's second laws with respect to rockets. All right. I'm hoping that next week we can set something up so that you can build a bottle rocket. Please collect a 2-liter bottle, and then we'll talk about trying to find time to do some sort of launch. Okay, because that's one of the highlights for most kids in term one. So when we start trying to calculate the acceleration of a rocket, there are a lot of things that we need to keep in mind. Remember, acceleration is a measure of how much speed increases per second, and it can be calculated using this equation we've just given you today. Okay, so if we take a look, all right, at F equals ma, we can solve for acceleration, which is going to be equal to force divided by mass. Okay, so newtons, remember, is a kilogram meter per second squared divided by kilograms, which is a mass. They'll cancel, which leaves us with meters per second squared, and that's our A for acceleration. Now, one model rocket has a mass of 50 grams, and a rocket engine produces 5 newtons of thrust for 1 second. So let's go through here. Notice that we have 5 newtons. There's our force. 1 second. There's our time. And we have a mass of 50 kilograms. Okay. So when we go ahead and try and solve for acceleration, we've got 5 newtons divided by, right, our mass of 50 grams. The Newton, remember, is a kilogram. So it's, again, really important that you keep track of your units so that you can do the appropriate canceling. So if we want this in kilograms, we're not going to be able to use our 50 grams. Okay, we're going to have to convert that 50 grams into kilograms. So we can move our decimal 1, 2, 3, 0.05 kilograms. Okay. And then we simply go ahead and solve. So that would end up, see, our units are going to cancel out to 100 meters per second squared. Now, when we go ahead and take a look at that, we have to think about how much we're actually getting, because it's tempting to just say, oh, look how fast we're going. But you have to remember, and this is where your free body diagram comes in, that if I have my little rocket here, we have our thrust, which is going to go this way, 5 newtons. But we also have to remember that gravity is fighting our rocket at 9.8 meters per second squared. Okay, and this is going to go ahead and determine our weight. So 9.8 meters per second squared times our mass, which is again 0.05 kilograms. And that's going to go ahead and give us 0.49 newtons. So we have an opposing force. So our net force is going to actually only be 4.51 newtons. And then we're going to go ahead and calculate using this number, which is not going to be as nice and round as the 100 meters per second squared. Okay, so divided by 0.05 again, and that gives us approximately 90 meters per second squared. That means every second, the speed of the rocket increases by 90 meters per second. This is 9 times the normal acceleration due to gravity. So we're seeing some pretty major forces applied to that tiny little rocket to get it to accelerate that fast. Okay. Now, what if we tried to ramp up this same sort of calculation to an actual rocket? Okay. Say the rocket that's going to go ahead and launch the space shuttle. So take down whatever you need here to understand the basic process of calculating using Newton's laws. And again, as I say all term, units, 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 units. And then we'll go ahead and try and do the same thing with calculating a space shuttle. Okay. Okay. So let's go ahead and take a look at doing the same sort of calculation, but with a real space shuttle. Okay. The same method can be utilized. The space shuttle mission that launched on February 24th, 2011 was called STS-133. It had a liftoff mass of 2 million kilograms. Okay, let's keep it in kilograms, but that's about 2,000 tons, which means the total weight at liftoff is 2 million times 9.8. Remember, meters per second squared, to go ahead and get about 20 million newtons or 20 meganewtons. The thrust of each of the big white solid rocket boosters on the side was 12.5 million newtons. But remember, there are several of them. And the three main engines at the tail um, that looks a bit like an airplane, the Space Shuttle Orbiter, has a combined thrust of 5.5 million newtons, which gives a massive total of 30.5 million newtons of thrust. Now, first things first, we have to get our net force. So you'll notice down here at the bottom that we are going to go ahead and take our thrust, okay, which is the 30.5 million, and we're going to subtract the weight, which is 20 million, to give us a resultant, okay, or an F net of 10.5 million newtons. Now, we're going to go ahead and use that to go ahead and do our calculations. So again, we're taking a look at F net is equal to the mass, which we just said was 20 million. Yeah, it should be, that's the weight, mass. So it should be 2 million. Yep. Okay, in terms of kilograms, this is going to be 10.5 million. Oops, it's not quite right. And this is going to be newtons times acceleration. So we divide both sides by 2 million kilograms. And that's going to leave us with an acceleration. And since it's kilograms, that's going to leave us with meters per second squared. And we end up with 5.25 meters per second squared. So if we compare that number to what we had on the previous slide, okay, we're looking at quite a different amount of acceleration. Okay, quite a different amount of acceleration. So even though we have a lower acceleration, we're able to get a bigger mass up into the air, but look at how much thrust that requires. 30.5 million newtons. That is a huge amount of force to go ahead and get a space shuttle up into space. Okay, so let's go ahead and really quickly compare these two just so you kind of get the idea. But the acceleration of the model rocket was 90 meters per second squared. Think about how light it was. That's why we were able to get there. That's far greater than the space shuttle at 5.25 meters per second squared. But there's a huge difference in the motion after launch. First of all, the model rocket had only enough propellant for 1 second of thrust, and after that first second, it reaches its maximum speed of 90 meters per second, of course, ignoring a little bit of drag and mass change. But after that first second of thrust, the model rocket starts to lose speed and gravity starts to pull it back down. We fire for longer when we go ahead and take a look at the space shuttle because these solid rocket boosters have enough propellant to last for 124 seconds. This means that the space shuttle accelerates for more than 2 minutes before the boosters separate. As the shuttle uses its propellant, it also becomes lighter, which also increases acceleration. And by the time we've burned through that 124 seconds, the shuttle has reached an altitude of 45 kilometers and is traveling at about 1,380 meters per second. At this time, once all the fuel is consumed, the SRB separates away from the external tank, the big orange part you're used to seeing in videos. Fuel continues to be pumped into the three main engines for another 6 minutes. Acceleration continues until the Space Shuttle orbiter eventually reaches a speed of about 28,000 kilometers per hour and an altitude of about 300 kilometers. This allows the orbiter to leave the main part of our atmosphere and orbit around the Earth. So I'm going to go ahead and let you finish by watching a rocket launch. Try and listen to the velocities that they're talking about, and then you guys will be on your own. All right, so enjoy this video. Thank you guys. Take care of yourselves. Stay healthy, stay safe, and I'll talk to you soon.
Ten seconds. We have a go for main engine start. 6, 5, 4, 3, 2, 1. We have booster ignition and liftoff of the Space Shuttle Discovery, lighting up the nighttime sky as we continue building the International Space Station.
Houston Discovery, roll program.
Discovery. Commander Mark Polanski confirming Discovery rolling on course for a rendezvous with the International Space Station. Speed 1,000 miles an hour, altitude 1 mile, downrange 4.5 miles from Kennedy Space Center already. Three good engines throttling back to 2/3 of the rate of thrust. Passing the air at maximum dynamic pressure, about to go supersonic. Here's a view from the external tank camera.
Discovery Houston, go at throttle up.
Go at throttle up.
All systems remaining go for Discovery. Altitude 8 miles. Speed 1,700 miles an hour. Downrange 10 miles from Kennedy Space Center. Minute and a half since launch, Discovery already consumed more than 2.25 million pounds of propellant. It now weighs less than half that it did at liftoff. Altitude 18 miles. Speed 3,000 miles an hour.
Notice that is calculating in the loss
Already
of weight
22
as we're
miles
going
northeast of Kennedy Space Center. Three good engines, 3 good auxiliary power units, 3 good fuel cells. Booster officer confirms clean separation of the 2 solid rockets. Discovery's 3 engines now powering the second stage. Discovery's orbital maneuvering system engines firing now to assist the climb into orbit. They'll fire for about 1 minute and 37 seconds.
Discovery Houston, 2-engine Maroon.
2-engine Maroon.
That call means Discovery can perform a transatlantic oceanic landing at Maroon, Spain, if required. 3 good engines, 3 good auxiliary power units, 3 good fuel cells. Speed now 4,500 miles an hour, altitude 45 miles, downrange 78 miles from Kennedy Space Center.
Okay, guys. Once again, take care of yourself. Talk to you soon. Take care.